Boom. So I had a question from Mr. Alexander. Is everything okay?
Jose said for an outlet.
Oh, okay.
I was just saying.
Oh, no, it's cool. I was just making sure it's okay. Oh, they really, you can plug stuff in there?
I mean, there's outlets.
There are. Whether or not they work, we
That
can see.
yeah.
So one of the problems in the web work, like problem three in the web work, probably everybody has the same one. I gotta stop looking at Vincent's pizza. Smells so good. So, and Alexander, remind me if this is kind of what, it's something like this, right? They give you this as the solution.
Yeah, they give you the Y. And
Okay.
And it's just trick.
You've done
like
this
that.
one. Yeah. Okay. Awesome.
Yeah, I'm sorry.
No, it's cool. And they say, they essentially want you to verify that this is a solution to this equation. And I think the concept of what is it to be a solution to this equation was what maybe Alexander, you were like, I'm not quite sure if I understand what it is
I got
I'm
to
doing.
the right answer, I just didn't understand the differential equation relationship part.
Yeah, so like this
That
part here.
Y prime.
I mean, in some ways, we could look at it like this. Let's suppose Y is position, right? And this is a mass spring system here, by the way. This is pretty close to the thing I developed the other day, except I had an X. So it's literally this one, just with a Y, this mass spring equation. But so if we let's do it, I like X better. If X is the position of the mass spring, however you spell that, and then X dot would be what?
The time.
Velocity. Yeah, that's velocity. Does that sound right,
Yeah,
Alexander?
that's velocity.
Okay, cool.
Yeah.
And then X double dot is what?
Du, dt,
It is that. It is that. But what is it in terms of?
dx, dx.
No, in terms of the next.
Position over velocity. Acceleration.
Thank you. So good. So let's take a look at this. Let's just look at this in terms of those ideas. We could rewrite this like this, right? And so I could look at this and say that the acceleration of this system at any particular time is always in the direction opposite to its position. So that would be one way I could kind of gain a rough understanding of what like physically this means. Is that the kind of thing?
I like seeing it like that. Yeah.
Okay. Cool. Does that help maybe
does.
make it
It
feel
does.
a little
I
better?
want to hear more, but I'm with you.
Okay, cool. So, if I had this equation, I don't think I did this, equals 0. Same kind of thing. Here I've got the acceleration is actually 4 times the position in the opposite direction. If I'm just thinking of it like that, but I can tell you the solution to this thing is x of t is c1, and c1, I don't know what it is. It could be anything, and it's still going to be a solution. Cosine of 2t plus c2 sine of 2t. So notice it's a little bit of a different solution, but to prove it was a solution, I would have to go through and do all the machinations of derivatives. I have to go through these. So that's going to be negative 2 c1 sine of 2t. Does that sound good? What's the next one? What's the derivative? You weren't just telling me it looked good, were you? 2c2. Heard it. Cos. Why is the 2 coming up front? Close. Chain rule. Chain rule? Yeah. And it's that thing you've got on that sheet in front of you.
Say it's a form. Yeah.
KT, right? It's one of those guys, and then the K comes out in front. Oh, we didn't do that. We had to do the integral version. So I got to do one more derivative. What's the derivative of this?
Minus 4c cosine
Beautiful. So good.
minus 4c2
Thank you. So crank out these derivatives and notice that when you add this to this, everything cancels.
Yes.
So that means this is a solution. It wouldn't be a solution to this problem because now I've got, x dot. Now I've got like this x dot that's going to show up in there. So if I plugged all these things into this left side, I would not get a 0. They would not cancel. You can kind of roughly play that in your mind. You're going to get some stuff out. So really in that problem, Alexander, it's just mostly about, do I roughly understand what it means to be a solution to that? I wouldn't worry about understanding the equation too much.
I wasn't thinking about it in terms of like the derivative and like looking at the derivatives, and I just, yeah. I like the x equals negative x.
That's
That's
nice.
how I thought about it at first.
That's
Because
cool.
just you solve for one.
Oh,
I didn't think about it in any derivative sense.
Gotcha.
So, but
This
now,
feels a
now
little
that I
better.
see it though, it's the same thing. So I gotcha.
Outstanding. Cool. So one of the things I had asked you today was bring your laptop so we could do a little bit of exploration. And so I'm kind of hoping we can do that. And I'm going to need you, I don't have my laptop with me, of course. I didn't bring mine, of course. I wonder if I can plug my, no.
You can.
I can, but I can't because it's
Oh.
recording.
I mean, unless you want to do a screen recording.
I wonder if I could I plug this into the HDMI?
Is it USB-C or Lightning?
It's USB-C.
Yeah, they definitely
Yeah.
they give a USB-C input.
Does anybody have a USB-C to C?
I have a USB-C.
Oh.
USB-C. You need that. Wait, but it's two USB-Cs though.
No, that's
Does
correct.
that work?
If we have USB-C here,
Oh.
I don't even see anywhere in there besides Ethernet and outlets. Is there a computer in this room? Oh,
Put it into that. Just plug your phone into that. Yeah. Yeah. See what that does.
yeah, let's see what that is. That's pretty exciting. What a notion. And then the turn the power, we did this show before once. This is great.
Here. USB-C. That one USB-C.
There you go.
Oh my God!
I don't
Sorry. It's good, you woke up. Not for false sleep today,
I'm
buddy.
awake. I just
Sorry.
gotta focus on something else. No, I got this, not the T.
Brave.
I got this specifically for this
It's
class.
For math class?
It's so good. I still use Google to search, but.
It's just last class, I just felt like I was like,
Anybody else play Clash Royale?
I'm not a Clash guy. Not a Clash guy. My buddies love it though.
I have
into
that.
it. I feel like you had to either get into it in 2015 or you're just not into it.
That, really?
That's how
I got into it last year, so.
So, well then I'm obviously very wrong.
Yeah,
If you
well,
turn it sideways, does it also turn sideways something?
oh.
Oh.
That's amazing. That's actually pretty great. Okay, all right. So that app that's on in the world class, the way I find it is I know it's Bluffington Slope Field.
File.
There it is.
Bluffing. Should we go here too?
Yeah, please go there.
Bluffington.
So, oh, this is fantastic. This is like a whole new world we've entered here. Absolutely freaking beautiful. So, let's take a look at some more involved equations than we had last time. We are going to stick to first order equations in here. And what first order differential equations mean, the highest derivative is the first derivative. So, first derivative is highest level. So that one that we started off talking about at the beginning of the hour, the mass spring, that's a second order because it has a double derivative in it. We're not going to deal with that. That's like a whole semester's worth of thinking. First derivative is highest order derivative. So let's take a look at something a little bit, oh man, I just realized some really awesome stuff we're going to take a look at. So, let's take a look and see how to use this app. Yes, sir.
You just wanted to ask you want to Type-C charger for my laptop. Phone charger.
Oh, it's okay.
Soon enough,
Yo,
it's gonna be black.
Wait a minute, hey Jack, guys, hold on, I'm sorry, I'm having.
Type-C charger for my laptop. Anyone have?
Yeah, does anyone have a spare charger
What
and
kind
not
of charger
using
is
it?
it?
Or what?
Apple Type-C.
Type-C.
I mean, I have a Type-C cord.
Outstanding. Can we get in here? Is this got?
Type-C.
Yeah.
This is Type-C.
Nice.
USB.
Oh, like the laptop charger Type-C.
Oh, well, it's Type-C.
Yeah, it should still.
It should work.
It's just still charged. Is that the right one?
It'll charge slow, but. Yeah, it's gonna be pretty slow,
My
but.
bad.
It won't turn
It'll,
on.
yes, we just wanna keep it alive. Keep it on support. I'm curious if the power, does it look like it's charging?
Oh.
Nope.
It might need that like 40 watt or the 20 watt.
I think so.
Alright.
Do you have a phone?
Yeah, I just.
Yeah, go with, yeah, we'll both use our phone today. Oh, no problem. So we're gonna enter this into this app, and I wanna show you how to do that, because I'm gonna ask you to do some explorations from time to time. So first off, notice how on the left side of the screen, it says ODE, and then it has the derivative of y with respect to x is x plus y. But we can change the variables, and so click on that equation, and we can go down to variables, and we can choose our favorite pairings. So dx dt. And it just helps sometimes in terms of the thinking. And then we can adjust the system here to be x minus x squared. And I need my caret. Where's my caret? Was it in the other page? Do you see caret on here?
That's on the first page, I'm pretty sure.
I think it's in the
Oh, it's in the second page.
Yeah.
Oh, there it is, okay, yeah. And I should have a lowercase x,
called
it's
caret?
sadly caret,
Yeah.
K-A-C-A-R-A-T.
Huh.
So,
Carat.
Carat, karat, yes. Why does it keep capitalizing?
Because it's in my phone.
Yeah, yeah, that's probably spot on, there we go. So x minus x squared, and then I hit done, and it instantly adjusts the slope field. Do you want me to review what that slope field is? Does everybody kind of understand what they are seeing there?
Totally.
We're good?
Yeah, all good.
Cool, so just, and I will kind of just like really quickly, where did these lines come from, just to refresh, make sure. So this is the slope in terms of the tx plane. And to compute the slope at any point, you just use this formula. Notice it only depends on the x coordinate, which here is the vertical axis, right? This x here acts like our y normally does.
Oh, yeah, because T is.
Yeah, because T is the horizontal
Yeah,
axis.
yeah,
So this is saying that the slope only depends on the x coordinate, the vertical coordinate. And you can see that by looking at this. Look as along horizontal lines, the slope is identical along any horizontal line. This is called an autonomous system. So autonomous means free of time, or not dependent on time. It has time in it. Autonomous, I wish we could be free of time. Autonomous system or equation, probably equation, we don't have more than one right now. Autonomous equation, the state is independent, the change in state, that's a better one. Change in state is independent of time. So let's think about how we would use this. And we're gonna actually get into the nitty gritty of doing this today. If I started right here, you kind of, remember our arrows always point to the right. They're either up to the right or down to the right. So as I move this way, I move down. And then the minute I move away, the slope changes. So the path would kind of go like this. Each one of these lines is a tangent line to a particular solution. So my solutions will always perfectly hit one of these lines as a tangent. Look here at 1. Notice how a little bit above 1, it's moving toward 1, a little bit below 1, it's pushing me up to 1. So I suspect there might be an equilibrium here, right? Kind of the flow, you gotta think flow. And in fact, there is, because if we do a little algebra, we can factor an x out of this, and we see that it's actually this. So now notice that x dot is equal to 0. In other words, the change is purely horizontal. So this is purely horizontal change. Is going to happen when what? When x equals what?
0.
0,
Yeah.
yeah. Or what else makes this right side 0?
1.
1. So these are equilibrium. These are equilibrium solutions. If x is ever equal to 1, as we see right here, and it's not showing because we don't have enough little grids, but what's cool is you can click on this graph, so if you just touch a spot, you can see a different solution curve. So let me just get a group of them. Isn't that nice? How that works. So we're getting these various solution curves here, and it starts to see, you can see the equilibrium a bit better right there. Remember, equilibrium is a state I tend toward as time moves to infinity. It's your end game state. We also have one at 0, but it's a little bit different. Right? Notice how the arrows move you away from that equilibrium at 0. And so if we click a few more on here, you see that things that start near that solution tend to move away. And things that start near the top one tend to move toward it. And I like to put a bunch on there because it looks really pretty. So we have these two equilibria. We have one at 0, we have one at 1. This one is stable. This one is unstable. Do you remember that analogy, how we talked about that? Unstable equilibrium is precarious, any slight motion, and Alexander and I were talking about this. It's a high energy equilibria, high potential energy. Yes, sir.
No, I was.
Oh, you're cool. Okay, cool.
I was looking at.
I was like, wow, and now the question's not coming either. So that's an unstable versus stable. Low potential energy, high potential energy. So I want to be able to do this without this app. Let's talk about how to do that. We're going to briefly talk about something that's maybe in a book, I'm not quite sure. I look at books so rarely that I just know what the flow is. But what I want to look at is what's called a state diagram. So here I'm going to put x dot, that's the rate of change, and here I'm going to put x. Now, I'm going to graph that thing like it was y equals x minus x squared, and get a graph of it here. So if I did have y equals x times 1 minus x, what would that shape be?
Is it a line?
No. Look at the, boy, this is going slow here. Okay, let's just, it's this. Yes, it's a parabola. Thank you.
I was like, no way.
There's no way.
It's a parabola, right?
Because of the x squared.
It's x
Yeah,
squared.
because the x squared.
obviously.
Does it open up or down?
It'll go down, it's negative.
Oh, we know stuff.
Yeah.
Where does it intersect the x-axis?
At x.
What x? We just solved that, right? We know that
Oh,
the output is 0 when x is 0 or 1. And we know it opens downward. Yeah.
It's a basic math, it's the hardest part.
It's a stumbling block often. Does that picture make sense?
Yeah, it does, I agree with you.
Okay, so if y actually represents the velocity of the particle x, or the particle at location x, this axis now becomes the velocity axis. Velocity axis. So this thing is really just the state of x right here. This is the position of x. It's the vertical position over there. Notice that in this region, x dot is positive between these two. So that says that I have positive velocity. And that means my position increases as time moves on. X is always increasing. And you can see that right here. Here's 1, here's 0. Everything in that band is moving upward. Everything in that band is moving toward 1. It gets asymptotic as we move this way, but everything is moving up there. Whereas in these other regions to the left of 0, the graph x dot here is negative. And that means my velocity is negative. So negative velocity means I'm moving this direction. What about out here? Is that positive or negative velocity to the right of 1? Negative. So this is flow toward this direction. So I can actually take that up there and make not just that flow picture there, but I can make a phase line which only shows state. And in that phase line, we're gonna show x, 1, and let's see, what was that? Positive in here, negative here, negative here. Now watch this. This was an equilibrium. Since it's unstable, I'm gonna use an open circle. Since it's stable here, I'm gonna use a closed circle. And this now tells me everything I need to know about that system. I really can understand it completely by looking at this. Well, mostly, I don't know the exact shape of those curves, but I can easily move from this to that, a rough approximation of that picture. So I'm gonna ask you to do this now. And I'm gonna show you, I'm gonna give you a tip. So let's say we have x dot. I like to use x instead of y, just because it's more physicsy. Let's say we had x times 1 minus x times x minus 2. Now, I'm not going to ask you to graph this by hand because I know that's not going to go well. Probably, right? I mean, I'm not trying to be insulting. But if I asked you to graph this by hand, y equals this, how would that go? We might be able to get there in a while, right? Where are the equilibrium? What are the equilibrium solutions to this differential equation? Where is the velocity 0?
1 and 2. 1 and negative 2. Negative 1 and 2.
1, 2, also 0. Yes, exactly. I have 3 equilibria. Does that make sense?
Yeah.
Okay, good. I'm seeing that.
Wait,
Awesome.
why is it not negative 2?
Well, if I put a negative 2 in here, I'm going to have negative 2 here, 3 here, and then I'll have negative 2 minus 2 here. Does that make sense? So one way you could think of this, Jose, is you could say, well, that's 0, x equals 0, or 1 minus x equals 0, or, and break it down into a couple simpler things to help your brain a little bit, and then any one of those solutions will make that 0. Does that make sense? Okay, cool. So I have equilibria here. Now my question is, are they stable or unstable? So what we're going to do is we're going to get Desmos. And we're going to check this in this graph, but also now open up Desmos.
I would look up unstable.
What's that?
I was about to look up unstable instead of Desmos.
All right, so open the graphing calculator, allow Desmos to switch apps, absolutely. And instead of x dot, we're just gonna put y equals, so we're gonna say y equals that equation, which is x times 1 minus x times 2x minus 2, is that what I did? Yeah. There's my graph. Oh, we all getting that graph pretty much? Yeah, cool.
Yeah.
Okay. So now I'm going to copy it up here because I don't care about the details. All I care about is it positive or negative. So it goes like this is 1, and this is 2. You can see this is not a precise picture I've done here. That's pretty shitty units. So, what will the flow be in this region, left or right? Is x increasing or decreasing to the left of 0? What's the velocity, positive or negative? Positive, so it's moving to the right. X is increasing here because I have a positive velocity. So your position is increasing. What about this little pocket between 0 and 1? We increasing or decreasing? What's the sign of x dot in here?
Increasing.
Did you say decreasing?
Yeah.
Yeah.
Is it wrong?
Do you see notice that in here x dot is negative, right? It's underneath.
Sorry for being late.
It's all good. Little later than normal. So x dot is negative in here. Does that mean I'm moving left or right? Is x increasing or decreasing?
Decreasing.
Decreasing. What about
Increasing.
increasing? Here?
Decreasing.
Awesome. So now I can classify the equilibrium. What is this one, stable or unstable?
That's stable.
Stable, because if you move to the left, it brings you back. If you move to the right, it brings you back. So that is stable. I'll color it in solid.
Unstable.
Yeah,
Yeah, that's.
because any slight move
Yeah,
away
yeah,
from
yeah.
there sends you away.
That's not, I just wasn't anticipating you to ask for that one right there, so but yeah, I can still take my
That's
answer.
an hamburger problem.
The hamburger problem?
Oh,
What?
I'll pull it up for you, don't worry, keep going.
Okay. Stable or unstable? Stable. Now I totally understand the system. In fact, I could actually really quickly sketch the flow. Actually, don't worry about it. I'd rather have you watch this, Alexander.
Alright.
Yeah, I'd rather have you be here. We'll look it up after we get done with some stuff. So I can take that picture and roughly convert it into the t versus x picture. And let's see how to do that. I know that I've got an equilibrium at 0. So I'm gonna say, I'm just gonna put a little dotted line here, because this is x equals 0 is the t-axis. So at x equals 0, once I'm on there, I stay on there. And we'll check this out in our other app, just to make sure we got this right. We also have an equilibrium at 1, so I'm gonna put a little dotted line there. Once I get on there, I stay on there. Because when x equals 1, x dot is 0. You're not moving up or down. And then lastly, we have x equals 2. And that again is an equilibrium. So let me stop. Does that make sense?
That does make sense.
Good. I know it doesn't quite make sense to you, but you guys good? Yes, sir.
So why are all the arrows going that way?
Flow time is to the right, so the legend goes. So underneath, when x is less than 0, in other words, down here, now keep in mind, this axis here is this one right here. So you can kind of take this picture and kind of flip it up to get like that. There's very different information represented, and what I want you to get good at is moving back and forth between these. So down here, x is increasing. In other words, x dot is positive right here. That means the arrows all kind of point up, so I'm just going to make a rough approximation. In this region, that's this guy, x dot is negative between 0 and 1, so it looks like this. Here it's positive, and then here it's negative again. So now I've got a rough flow in the plane. I could probably make some guesses. Now, one thing to keep in mind is you always approach or leave an equilibria asymptotically. So you can never cross an equilibrium, ever. You can only approach it. And so down here, this is probably the way. This one here, let's see, as I move out this way, it's gotta be like that. But as I move out this way, I have to approach asymptotically. So like that. I have to leave asymptotically and approach asymptotically. And then up here, you've got this. So let's take a look. Let's get the app out. you're gonna want your laptop or your phone, and you wanna go to that,
This month?
not yet, we did, so now go to the Bluffington, it's in the announcements, I put a link up in World Class. Let's see, so where is that guy? Yeah, so enter that equation in there, and we'll check it out and see if I did it right. What do we got there? I hate that it capitalizes on the phone.
But if it was just all capital, then it wouldn't be an issue.
Well, that's a good point.
Oh, no.
Does it look about right? Yeah, a little steeper down below than mine, but the rough feel of it is pretty good. And I'll just hit enter. Oh, yeah, good question. So to clear those lines out,
I refresh, but then I have to re-enter.
yeah, that sucks. You know, there's a better way. If you go to the initial points tab,
Oh, clear all curves, yeah.
Yeah, that'll do it for you. It's all good. All good. Yeah, this is a great app. This is like ancient technology computer-wise. This thing, I've been using this for like over a decade, maybe even longer.
The app, the bluff.
This app, the Bluffington app. Yeah. It's got a lot of cool stuff. Do you see that RK4, h equals 0.1?
I do.
We're gonna understand what that is today, roughly. And so yeah, so I did an okay job just estimating it. I have a question for you. Could you please sketch one of these direction fields, but do it for something a little freakier? Oh boy, you're gonna like this. This is gonna give me time to go pee. This will be good. Like throwing down, knocking down barricades to slow you down. Gotta jump over them. Closing the doors. That diffie cube. Step one. I want you to figure out where x dot equals 0. All you have to do is look on that sheet that I see everyone has out. They're always referencing with their graph of sine on it. Beautiful. Or maybe it's in your head, and that's 10,000. Good man. So first off, where are the equilibria? And then what you can do is plot your x dot versus x here. So now make a sine graph on this phase plane. Phase planes are all about state. They hide the time. They hide the autonomy part of everything. Go for it. Find all the equilibria, classify them as stable or unstable, and then if you've got the energy, make a D field. This shouldn't take too long. I'll be right back.
Because you can like just like stretch it forever. Yeah, I think we should probably just like not one on the. Maybe, I don't know, but I agree with you because it would be 0 at like multiple different points. At least x would be 0 at multiple different points.
and if you said pi over 2, I know you were thinking 2 times pi over 2. And this is over pi, and this is minus pi. Yeah, some of us think in halves. That's okay. And that's minus twice pi. Now, what's this one?
Pi over 2.
Yeah.
3 pi.
3 pi over 2. Good shit. There we go. And so on and so forth. What's that?
2 pi over 2 divided.
Exactly. Exactly. Yes. So this is my phase plane image of this system. Very complicated. This is weird. We actually, this would be really hard to solve. I know we don't even know how to solve them yet, but we will soon. What is the flow between 0 and pi? Is it left or right?
Right, yeah.
Yeah, because x dot is positive. Yeah, exactly. X dot is it's above, and this is our velocity. Right? This is our velocity axis. And then here, left, and then right, and we get the rhythm going.
Yeah.
And so how many equilibria are there?
There's 1,
2.
2,
Keep
3,
counting.
3.
Keep going.
Well, infinity?
Infinity.
Yeah, because there's multiple periods of pi.
Yes.
Sine, I meant.
Yes. That's perfect. Yeah. It's like so we have equilibria.
But it's only when x is 0, right?
It's when x dot is equal to 0. Equilibria at x equals a multiple of pi. I'm going to put a k there. And k is equal to 0, plus or minus 1, plus or minus 2 on a. Does that sound good?
Yeah.
I have stable equilibria here, probably out here again, then right, like I have to go out a little bit more. There's 3 pi, and that'll be like that. There's a stable, there's an unstable. What do we got here? Stable. Unstable, is that cool with everybody, or does that need some explanation?
No, I'm good with it.
Anybody else need an explanation?
For what?
The stability.
Just for the arrows, I drew it, I'm saying.
Oh, no.
Okay, cool, all right. So, we have stable equilibria at where? How would you phrase that? How would you communicate?
When x not is negative, or no, the other coordinate. When,
No, I wanna list the points off. Where are they? Give me the coordinates. Where are they stable?
0.
Zero's unstable.
3 pi over 2.
3 pi over 2 isn't in equilibrium.
What?
Pi? Where's another?
3 pi,
Not 2 pi,
3
but 3 pi, yeah.
5 pi.
5 pi, thank you.
And so on, so on.
And so, what about this way?
Negative pi.
Negative pi. How could you say that? And then forever that way too, right?
I have a question.
Yes.
I fell behind somewhere, and that 2 pi is not equilibrium.
2 pi is an equilibrium, it's just not a stable.
Oh, because it's going up positive. Oh, right. Yeah, never mind. I didn't fall behind. We're good.
No, you didn't at all. You just needed to ask
Yeah,
a question.
Yeah, it's all good.
So how would you describe this to someone? I'll take a mathematical description or just, what's it?
Odd numbers.
I love it. At odd multiples of pi. Where are the unstables at? There we go. That's how you do school. Unstable equilibrium at even multiples of pi.
That is how we do school.
That is how you do school. That's how I did school. And so if I was gonna do a phase plane, I'm gonna first mark off all my equilibria, not phase plane, excuse me, just the flow plane. We got xt, so at 0, if I'm on 0, I stay on 0. I'll just kind of put arrows to show that, because that's an equilibrium. If I'm at pi, I stay on that, so that's an equilibrium. And then 2 pi, there's just gonna be these lines every pi. And they are horizontal solutions. Same down here, negative pi. So now let me ask you this. Between these two, am I flowing up or down in this band? Between 0 and pi. up.
Okay.
Because I can look at that hump and see the next dot is positive. So in here, we're flowing up. What about below it?
Down.
Yeah. And now I can really see the unstableness, right? And then I could sketch in a few trajectories if I wanted. Yeah. And if I put that into the critter maker, the Huffington slope field maker, I would see a plane filled with these beautiful alternating, kind of like that, but just alternating forever and ever. Does this sound good? Cool. Excellent. Let me give you one more here. So that's good. That was really good. I'm going to give you a homework set to think about this stuff with. I don't have it together yet. I think this stuff is very cool. So I was kind of thinking that the next exam might be like next Friday, but it could be the following Monday too. I kind of want to.
Not Monday. Come on. Please.
Really?
Yeah.
Is that really bad?
Yeah,
Okay.
that's really bad.
Yeah.
No need to start off the week like
If
that.
Vincent thinks it's bad, then I'm definitely on board. Yeah. I feel like you would put up with a lot in school.
I don't
Yeah.
know.
Exactly, but yeah, I don't want you unhappy. I wouldn't want anybody unhappy,
We would be unhappy.
but I really don't want it. But we won't. So we won't do it on a Monday. How about that? I promise that. I don't know if we next.
I mean, unless you have to.
No, we don't have to. We don't have to do anything. We'll do what we want.
Great. No exams. Sounds good to me.
Yeah. I'm like right now I'm a little torn between wanting to show you something cool and
And what? What's the burger problem?
What's that? This is the burger. Last top one homework.
I'll do something cool on Friday. Sorry, I gotta like put it together. Otherwise it might be a bad story and I don't wanna tell you all bad stories. I wanna think about the story before I tell it. I have a rough sense, but I wanna make sure I got the details right. Let's talk about solving differential equations. So getting explicit solutions. To problems of the form x dot equals some function of t and x, or same thing, same rhythm, just different letters, y prime equals f of xy. This can get so tricky here, right? Because here x is an independent variable, up here x is the dependent variable. So just gotta keep that clear, and that might potentially be something you snag on. So if you feel yourself having trouble doing one of these, I bet you're thinking about the x run. That's just my guess. But we will assume we're only gonna do a very narrow class of problems. So we will only study what are called separable differential equations. I kind of want Alexander to be able to move forward in his homework. And this is what it's going to take. Separable diff EQs. They're kind of one of the simplest types. What it means is that we have dx dt, so again, that's just x dot, right? That's just the x dot version, equals a function of t times a function of x. Now this might look like a quotient if one of these is a quotient, but what it's basically saying is that you've got this pure t part and this pure x part, and I can divide one of the two out. You'll see what I mean when we get an actual example. Or the y prime version is I have dy dx equals a function of x times a function of pure y stuff. And the goal is going to be to basically separate the variables using simple algebra, usually division or multiplication. So our goal is going to be, first off, something you're gonna be very excited about. We're gonna treat this like an actual fraction, where I could split the dt off and the dx, and we're gonna treat this like it's a fraction, and I know you've been told not to do that probably ever. Somebody probably should have told you that at some point, whether or not they did. But we're gonna treat this like a fraction. And our goal is to use simple math ops to get the equation into the form. Let's do the x one first. I'm just gonna have some pure x stuff times dx equals pure y stuff, or pure t stuff, times dt. Or I'm going to have pure y stuff, dy equals pure, and this is going to make way more sense in just a second with an actual example, pure x stuff, dx. After we do this, we're going to integrate both sides. So the stuff we've been I'm probably screaming and bothering all sorts of things. I don't think it can get any hotter, so that'll be fine. So we're going to do that, then integrate each side. And that's going to be our solution. Get a solution. So let's do this. And once you see this done, you're going to absolutely understand what I'm trying to say. And I think on Friday I'll probably bring in an assignment for us to work on that'll push some of these ideas together, and then we'll just work on it together on Friday. So example. I've got y prime, I'll just go to y, I'll do both so you can see how this works, equals xy, x times y. So this kind of looks like this, but you need to make that first move. If you don't see the fraction dy dx or dx dt, you gotta convert it. So step one is to just note that y is dy dx. Replace. So this is going to be dy dx equals xy. Now I have to use, and this is where things might get a little funky from time to time, legitimate math moves to get this separated. And so like quite often people have illegitimate math moves, but we're going to get better at it. We're going to keep things chill. So could somebody tell me, how could I just get this dy dx to not be a fraction anymore? How would you just get rid of that fraction in this equation?
Get rid of one of the, do you still want dy and dx?
Yeah, we can't get rid of it. Yeah. What was that?
Multiply both sides.
Doesn't that get rid of dx though, or dy?
I'm going to multiply both sides by dx.
Oh, by dx. Oh, yeah, okay.
Does that make sense?
Yeah, I'm totally with that.
Cool. So that'll probably be one of your first things you want to do, is whatever that dy dx is or dx dt, flatten it out. Multiply through by the denominator. Next, I want to get all the x stuff by dx, and I want all the y stuff with dy. Well, the x is already over here. How do I move that y to this side?
Divided by y.
Yeah, look at that.
Dimensional consistency.
Is this looking good? We got this? We're good?
Yeah.
All right, hell, it's nice, right? It's like, holy shit, really? This is calc? All right, well, it is going to be calc. What's the antiderivative of the left side? So now I'm going to integrate.
dy over y.
Yes, that problem.
That problem is getting integrated.
Yes. What is so now let's do this. And you want to always add in a plus c. I would add the plus c in on the independent variable side. Just works out better. What's this?
Y,
No. Wait, what did you say?
Y,
I thought I answered correctly.
So let's make the
Well, let me get my sheet out.
+1, +2.
Exactly what I was.
Oh, there's the answer on my sheet. Can we do the right side? How about we start at the lower hanging fruit? What's that?
One half X.
Thank you. I was like gonna have to get a lounge chair to. Yeah, thank you. What is the left side? What?
Oh, it could be. Is it ln of y?
Yes.
Wow.
And
Hey, that was Jose. Give Jose credit for that, please. That was not me.
was that
Jose asked me, and I said that's probably accurate.
Jose? And in turn, I thank the sheet that Jose pulled out, right?
Maybe.
Maybe, yeah. Slap on absolute values, be safe. Yeah. So this is a solution to the problem. But you might be saying, I don't understand that at all. That expression is insane. What does that even look like? So what we try to do is isolate y. And this is where I am picturing lots of not fun happening. Could someone tell me how to rewrite this as y equals something?
E.
Oh, god damn, yeah.
E.
Try to not say god damn, not that I care, but some people care. Okay, that's good.
Multiply on, well, it's the natural, it's the ln, which is already like over something, so like,
Okay, so this relationship is equivalent to,
why are you using shapes, bro?
because we need shapes, bro.
E to the y. Is that what you're saying?
That is not what I'm saying.
Okay.
So let's look at this problem. Up here I've got absolute y in
Is
there.
it e to the half x squared?
Yes! That's why I got boxes, bro. Because I can lay that on top of there, this is what falls in.
Where?
Well, I get, like, why is, oh, yeah, okay, yeah.
Do you?
I do, we're just, it's the same relationship as that, like that
Correct.
whole thing, I just
Yeah.
didn't see that now, but now I get it. They're equal to, yep,
Good shit.
you're showing the same thing, I got it now,
Dig it.
yeah.
Love it. Now you see why I got the boxes too.
Yeah, I know, and now
Yeah.
now I get it,
All right, so. So I'm gonna show you some moves that are gonna be.
Sorry about the bro moment. It's on-
No, it's fun. It's all good.
It's not very
I'm hanging with
respectful
it.
to a PhD,
It's quite fine. We're all friends.
we're all friends.
All right, so that left side, I'm gonna leave like that. This right side, I want you to notice something you probably wouldn't have thought about, but the right side can be written like this. Yeah, moving backwards, yeah, because you would add the exponents.
yeah.
Now this is just a constant. It's C, I'm gonna call it C again. I'm absorbing C's. We did this once a long time ago, I think, it feels like it. But I'm just gonna call that C. If you don't like calling it C, call it D. Call it something else. I'm gonna call it C. And since C, now this C has to be a positive number the way I've written this, but if I strip off these, now C can be positive or negative. And that is in fact my solution, and let me prove it to you. It's a lovely looking solution now. So let's prove that this is the solution to this equation. So the first thing I have to do, let me put it back over here, is take the derivative. dy dx equals, what's the derivative of the right hand side?
1/2
Good thing I have a lot of chairs around today.
Is the question, sir?
What is the derivative of the right-hand side?
Oh, there's a form for this, isn't it?
Oh, there
There's
is.
a form
Yeah.
for this.
Isn't it half,
It's, that's
half
a
x
KX,
squared?
so like,
It's not a KX.
it's not.
No, isn't it just the same thing?
You just bring the exponent down and then keep it up there too.
Kind of. What do you do to the exponent?
Either 2 times you differentiate the exponent,
Yeah.
so it's gonna be x to the e.
X e to the 1/2. So, okay, so what Uthman is
I
summoning.
forgot how to do a derivative.
Yes, I do catch that. That if I have derivative of e to something, it's e to that something. So we kind of all knew that that would happen. But then Uthman was the only one who knew that you also multiply it by the derivative. That's the chain rule.
Right.
That's right.
Okay, so the right side, so the c, I just pull the c out, and then it's e to the 1/2 x squared times the derivative of the exponent, and I hope we can all agree that's x.
It is x.
Oh, good.
It is x. 1/2 times.
So now notice what this right side is. It's y times x.
Oh.
Yeah, pretty.
I just have a question.
Yes, sir, yeah.
How did you go from e to the c to c?
I just called this c again.
Oh.
If you want, you could call it d, a new constant,
Okay.
but just use c again. Think of absorbing, everything becomes c, yeah. Yeah? Your turn. Please solve this differential equation. So Alexander, now you can see how there's a hope of doing the rest of the problems.
There is definitely.
There's great hope. There is hope where there once was none. So let's see. So we had that. Let's change it up a little bit. Solve that. We'll keep it chill, right? Nice and chill. Is Uthman a common name? Is that a common name? I've never heard your name, your first name.
No, it's from it's like it's an Arab name.
Yeah, but is it a common?
Yeah.
Really? Interesting, wow. Oh, that's cool. Would you have a middle name?
No,
No.
it's really rare in Arab.
A middle name is, yeah. You got Uthman, that's pretty, that's perfect.
Every time I
Now
look
you're
back,
super,
I'm like,
I think you're good. I don't think it even
Oh,
sees you.
I know.
Like, what?
like every every lecture that we have, I just make sure I'm not gonna block the camera. I'm pretty sure it's like high enough. I don't even block
You're
it.
good, you're not even in there.
Yeah.
And then if you get it solved, let me know, I'll check, I'll give you a sanity check.
I don't know about this one.
And then my next question would be, can you solve for y in terms of x? And then my next question would be, what do the curves look like that are solutions to this? But you just solve it first. We'll worry about the other fun stuff. I'll put it into the app so we can take a look as well at the flow. You're right. You forgot the, yes, that's why you couldn't. That actually would be okay if
Yeah,
the C was zero,
yeah,
but yeah, good call.
And it just turns into, I don't know what to do after that.
I don't know how you got y equals x plus c. cause you had this, so this I agree with,
But not this,
and then,
cause like.
yeah,
square
cause
root
square
two-
root, this, remember the freshman's dream?
Oh, shoot, oh, I forgot the
We
C.
don't wanna be dreaming like that, there you go,
Okay,
perfect,
okay,
yeah.
That makes,
Yeah,
If there wasn't a C thing.
correct,
that would be
yes,
fine.
yeah, absolutely.
Oh, that's why.
Yeah. C.
Yeah, that's great.
I don't know,
Now,
that's
with, take the square root
I, we have to
of
take
both
the
sides if
integral
you
on
wanted.
both sides.
So, you could, so
Yeah.
y equals plus or minus square root
And then
of x squared plus c.
we have to integrate.
We don't know if it's the plus or minus branch, so, but that's our solution. That's it. But if you want to now push it a little further, what do the graphs look like? Because it's actually a well-known quadratic, I don't know how well-known it is, but it's a quadratic curve. So like parabolas, hyperbolas, ellipses, it's one of those.
Your T.
Yes, sir.
So when you got after the y equals all that part,
Yeah.
where did you get the x from?
This was the derivative, so I took this and I took the derivative of each side, Vincent. Does that make sense?
Yeah.
And then that was the chain rule on this guy.
Oh,
So let's do this guy. First step, get myself a fractional differential. Definitely seen that. It's great, awesome. We got this as half credit. That's great.
Let's call it there.
Like so? Do we agree?
These are integrals, correct?
Yes, sir.
Okay, then I
Yeah.
agree.
Cool. Good, and I think I saw this a lot. So now, I would multiply through by 2 and absorb that into the c. That's 2c, but I'm just gonna say it's c again. So that you can have fun. This is like a really, it feels like you're being naughty, mathematically. You just like, who cares? Stuff it under the rug. So I love absorbing stuff into constants like that. It'll all be okay. And then if I was going to solve for y, remember that when you take the square root, you have to put a plus or minus, because you don't know where it came from, the minus version or the plus version. So the best we could say is this. Then depending on if what I know about y and x, if I know one point on this thing, I could figure out which of the plus or minus parts should be in there. But let's just not worry about that quite yet. Does this look okay? Jose?
So how did you get the half y squared equals?
I took the power rule. I took the integral of each side. So I did that. Power rule. Increment the exponent by 1, divide by the new exponent. Yeah?
Okay.
That one? Good? Yeah. Okay. Cool. Yeah. Awesome. What do these curves look like in the plane? I have a feeling I'm not going to get a lot of like buoyant answers about this. So I don't think you're going to be very forthcoming. You're going to hold out on me, even though you know what these look like.
Like parabola.
It is related. It is a family of hyperbolas.
Oh, it's the other, what is, you told us one time, what's it called?
It's a hyperbola. Because I could write it like this.
Oh, yeah, but
Yeah.
I thought you were saying something else.
So it's hyperbolas, and I know a lot about hyperbolas, and we're not going to talk about all that I know about them. But if c is positive, it's going to look like one of these. Ooh, that was bad. And if c is negative, it would be in this side or this side. So depending on c, I've just got a bunch of hyperbolas in the plane. And what this is saying is that if you take any one of these curves, so let me explain this to you. If I take any one of these things, you find out what c is, go to Desmos, plug that shit in, get one of these, pick a point on there. What is the tangent slope at that point? All I need is the x and y coordinate. So if this is the point 2, 7, right there, then the derivative there, y prime, is 2/7. I just use that formula. these things, they have all the information in different forms about each other. Does that make sense? Ish is good right now. Ish is good. What time is it? All right,
It's breaking. Pretty close.
Yeah, you must be sleepy after that pizza.
I mean, yeah, I was falling asleep, so rather like not fall asleep than
All right, Vincent just got you out of here.
Oh, thank you.
Alright, well,
It's only 5
I'm
minutes.
not done with Dr. P though.
Oh,
I'm gonna show you this hamburger problem.
okay, I want to see the hamburger.
And the
problem.
reason I'm
Oh, you bet. Thank you. So we'll keep this going on
This
Friday.
is a homework assignment, bro. This is literally a homework
Yes.
assignment.
Could you stop that for me?
Yeah, no
please?
problem.
So I had a